Okay, so far we have looked at the simplex algorithm, and that's all very well and good, provided the origin is in the feasible region. But if you think back to when we did graphical linear programming, sometimes the origin is not in the feasible region, such as this problem here. So what we're going to do in today's video is we're going to have a look at what's called two-stage simplex, and this is used when the origin is not in the feasible region. And it's called two-stage simply because there are two stages to this algorithm. The first stage will move us from the origin to the feasible region, and then the second stage will move us within the feasible region to the optimal vertex. Now, we have looked at solving linear programs like this graphically. It's a two-dimensional case. So what I've done is I've just gone ahead and done the vertex testing method on this program, and we can see that A is the optimal vertex with a p-value of 180. So that's what we're going to be working towards using our two-stage simplex here. So this is the vertex we're going to be getting towards, but we're going to start at the origin as we normally do for simplex. Okay, now the issue is this constraint here. These two constraints are no problem because the origin satisfies both of those. If I plug in x equals 0 and y equals 0, both of those constraints are satisfied. The problem occurs here. So we'll get to that in a little bit. So just as before, we're going to take our objective function and we're just going to put all our variables on the left-hand side. So the objective row will become p minus 3x minus 2y equals 0, just as it was with normal simplex. Furthermore, these two here, again, because the origin satisfies those, there's nothing different we need to do with these two constraints. So we're going to end up with 2x plus y plus a slack variable equals 100. And then we also have minus 2x plus y plus a different slack variable, and that's going to equal 20. So there's no problems there. Difference occurs with this one. All right. Now, because the origin does not satisfy it, we can't just pop in a slack variable. So if we were to do that, we'd end up with 2x plus 3y plus a slack variable equals 140, which looks like it might be okay. The problem is it's a greater than or equal to, not a less than or equal to. So we shouldn't be adding a slack variable here because there's no slack to take up. When you're at the origin, you need to be 140 above it. It's not a slack that you're pulling out, it's what's called a surplus. So this is actually wrong because we need to be taking up anything that is above the value of 140, not below the value of 140 as it would with a slack. So what we should do is we should do 2x plus 3y minus a surplus variable equals 140. This is looking better because now if 2x plus 3y is bigger than 140, say it's 200, then we can set our surplus variable to be 60, and that will take up any surplus in the constraint. So this is actually better. The problem is with this one is when you're at the origin, x is 0, y is 0, it requires S3 to be negative 140. But for simplex, we cannot have negative values for our variables. It just doesn't work. So we can't have that either. So what we do instead is we stick with this because we like this because the S3, the surplus, will take up however much 2x plus 3y is over the value of 140. So we're going to keep that, 2x plus 3y minus a surplus variable. But we're going to introduce another variable, which we're going to call A1, and that equals 140. And now this is good. We're happy with this. But we just introduced yet another variable. This variable is referred to as an artificial variable. All right. If the artificial variable is non-zero, then that means that the simplex solution that you are currently at is an artificial solution. It's not a real solution. And that's because we're not in the feasible region. So although it gives a solution, it is not a feasible solution, so we call it an artificial solution. And it's all wrapped up with this artificial variable. So what that allows us to do is, at the origin, when we start our simplex algorithm, we have 0x plus 0y. We can set our surplus to be 0, and now we can set our artificial to be 140. That means that we are essentially 140 units away from the feasible region, if you move directly in that direction. Okay. Our first objective would then be to get rid of all the artificials, and then that would leave us in a position where we are at the feasible region, and then we can move about within that to get to the optimal vertex. Okay, so this is what the constraint looks like. But did just hint, we do need to have another objective, because we can't maximize P, we can't look to do our objective without first getting rid of our artificials. So what I'm going to do is I'm going to say, I'm going to minimize a capital A, which is going to be equal to A1, which in this case I'm just going to call A. Okay. When this first objective is met, i.e. when A is 0, then the solution is not artificial anymore, because A is 0, which means we are in a feasible solution, or in the feasible region. Okay, so if we first minimize our artificial variable, then we can then look to maximize our objective variable. Okay, so that gives us a second objective that we need to complete. So we've now got two objectives. We've got our original objective up here for the linear program. We've got our second objective here, which is to get to the feasible region in the first place. And then we have our three constraints, the two normal ones, which were here, they were both fine, and then this new one here, which is a little bit trickier to deal with. Okay, so what I'm going to do with this is I'm going to fill out the initial tableau, and then I'm going to run the whole of the two-stage simplex algorithm for this problem. Okay, so I'll come back to that one. This one, we've got 1p minus 3x and minus 2y. So in our tableau, we can see now we've got 2 rows for our objectives, and then our 3 constraint rows. Okay, so that's new for two-stage simplex. So we've got 1p minus 3x minus 2y, no slack, no surplus, no artificial, and the right-hand side is 0, and there's no artificial there. Then our 2 constraints were these two. 2x plus y plus a slack is 100, minus 2x plus y plus a different slack is 20. So we can plug those both in. So 2x plus a y plus a slack is 100, and minus 2x plus a y plus a different slack is 20. There's no objectives over here. Okay. Now our artificial one, again, we've got a negative S3 as our surplus variable, not a slack variable, surplus variable. And then we've got our artificial variable as well, which I've called A, because there's only one of them. In the next video, we're going to look at a case when there's 2 artificial variables, and then we can see how the algorithm changes slightly. So 2x plus 3y, 2x plus 3y. Then we're going to have a negative surplus variable plus our artificial variable, and that's going to equal 140. Okay. All right, now this objective here, we don't want little a to be here. So what we really want is to bring capital A in terms of all the other variables, in terms of all the objective variables x and y, and our surplus variable S3. So you could rearrange if you wanted to. There is actually a little bit of a quicker way to do it, but let's just see the maths in the rearranging. A1 is going to equal 140, negative all that. So it's going to be A is equal to 140, subtract 2x, subtract 3y plus S3, because that's exactly what A is. And then if I bring it all across the other side, I'll end up with A plus 2x plus 3y minus a slack, surplus, equals 140. Which you'll notice is exactly the same as this objective, except A1 has been replaced with capital A, which makes sense because capital A is lowercase a. Okay, so that's nice and easy to do if there is one artificial variable. If there are more than one artificial variables, then you need to add multiple rows together, but we will look at that in the next video. In short, this row here will be exactly the same as this row here, except this 1 has moved to capital A. Okay, so that's a 1 there, nothing there. That's a 2, that's a 3, that's a 0, that's a 0, that's a -1. That's not going to be there because that's capital A, and then the 140. Okay, and that is our initial tableau. Okay, so now let's have a look at how we go about doing simplex on this. So there's our initial tableau again. Now, first step of simplex algorithm is to choose a pivot column. So we're going to do exactly that, except this time, because we want to minimize capital A rather than maximize capital P, we are going to have to choose not the most negative value in the objective row, but instead the most positive. Okay, think about it, kind of makes sense. If you want to maximize, you choose the most negative. Therefore, if you want to minimize, you must choose the most positive. Obviously, you can't pivot on the right-hand side, so the most positive is Y. Okay, so there's our 3, this one here. This is the reason we are choosing this column, because it is the most positive number in the objective row. Okay, we're doing the minimize A first as our first objective, because that will take us from the origin to the feasible region. We now conduct a ratio test as normal, which is the right-hand side divided by the entry in the pivot column. So 100 divided by 1 is 100, 20 divided by 1 is 20, and 140 divided by 3 is 143rd, which is bigger than 20. So this is the one that we are going to choose, because that's the smallest positive. Again, we don't want to overshoot, so we choose the smallest positive value from the ratio test. That fact hasn't changed, because we don't want to go too far. There's my pivot. Now it's already a number 1, which is good, because that means my pivot row is just equal to row 4. Okay, so my pivot row equals row 4. Okay, don't forget R4 is row 4 from the previous table. So I can just copy that row down. So 0, 0, -2, 1, 0, 1, 0, 0, 20. Okay, this is the pivot column that I'm choosing, so I want that all to be zeros except for the 1, which is already there. These ones will always be pivot columns, like so. S1 and A1 will remain as 1s and 0s, 1, 1 and 4 zeros. Okay, so those are the values that I'm going to get rid of. And to do that, I'm going to add multiples of the pivot row, which is now defined as this row, to the previous rows. So to get rid of that 3, I'm going to need to do row 1, and I'm going to subtract 3 times the pivot row. I'll get rid of that for me. The next one is going to be row 2, and then I'm going to plus 2 times the pivot row. The next one is going to be row 3, subtract the pivot row, and then finally row 5, subtract 3 times the pivot row. Okay, so those are my instructions on the left hand side there, which will help me to calculate all of this. Right, so get a calculator out just in case you make a mistake. 2, which is the previous entry, subtract 3 times the pivot element, which is -2, so that becomes an 8. That's a 0, that's a 0, that's a 0. Subtract 3 times the pivot, which is a 1, so that's -3. That's a 0, so actually that's going to remain as the same there, so it's nice and quick. And then 140. 140 minus 3 times the pivot, which is 20, so that brings us down to 80. Okay, and just carry on. This is exactly the same process as regular simplex. We're just adding and subtracting multiples of other rows. So this one here, we're going to have -3. We're going to plus 2 times the pivot row, which is -2, so that's a -7. Then we're going to have a 0 plus 2 times the pivot row, which is 1, which is just the number 2. And then we're going to have 100. Oops, sorry, no, we're going to have 0 plus 2 times the pivot, which is 20. So that's the number 40. Row 3, that's going to be a 2 minus the pivot, which is minus -2. Just be careful with your signs there. It's a positive 4, not 0. Going to have 0, subtract 1, which is -1. I'm going to have 100, subtract 20, which is 80. And then row 5, subtract 3 times the pivot. So that's going to be 2, subtract 3 times the pivot, which is -2. So that's an 8. In fact, this is going to be the same as the top row, isn't it? Same instruction, and it was the same row to begin with, so except for the A's. Okay, so that's completing one iteration of the first stage of two-stage simplex. We've not met the first objective yet because there is still a positive value in our first objective row, which means that A can still be minimised, which is good because it's currently 80. And because capital A is 80, that means lowercase a is also 80, which means our solution is artificial. We have not yet made it into the feasible region. Let's just have a little check of where we actually are. Capital A is 80, capital P is 40, Y is 20, X is 0, S1 is 80, S2 is 0, and S3 is 0, and A1 is 80. Okay, so that's all the values extracted from the table for our variables. And let's have a look at the graph. We have moved from the origin to here. So we've moved up because we've chosen to move in the Y direction. So we can see that we are still outside of the feasible region, which we knew that because our solution is artificial. At that point, the value of P would be 40. It's not a feasible value of P, but it is what the value of P would be at that point. Okay, so that's where we are at the moment. So let's conduct another iteration of simplex. Again, we're still minimizing A. We've not met that objective yet. So we're going to choose this column for our objective, for our pivot column, because that is the most positive value in this objective row out of these variables. Now we'll conduct a ratio test. 80 divided by 4 is 20, 20 divided by -2 is -10, and 80 divided by 8 is +10. So we should choose the smallest positive, which is that one. So that is going to become our next pivot. Okay. So row 5 then is the pivot. So PI is going to equal row 5 divided by 8. So I'm going to divide that whole row by 8 so that this is the number 1. So it's going to be a 0, a 0, a 1, a 0, a 0, minus 3/8, minus an 1/8, a positive an 1/8, and 10. We want to make this column 0, 0, 0, 0, 1. A will always be 1, 0, 0, 0, 0, and P will always be 0, 1, 0, 0, 0, and our other two columns, which are nice and quick, are going to be these two, because they are just 1 1s and 4 0s. 0, 0, 0, 1, 0, 0, 1, 0. And this one won't be because we're moving 0, 0, 0, 0, 1 from A to X. Okay, so that one will now be a column full of junk. Okay, our instructions. So to get rid of this, we're going to do row 1, subtract 8 times the pivot row. We're going to do row 2, plus 7 times the pivot row. We're going to do row 3, subtract 4 times the pivot row. And then we're going to do row 4, plus 2 times the pivot row. Okay, now don't forget that R1 is the row 1 of the previous tableau. R2 is row 2 of the previous tableau. R3 is the previous tableau. R4 is the previous tableau. But PI is R5 of the new tableau. Okay, so I've defined it. Pivot row equals row 5 over 8. Okay. All right, so let's fill out these values here then. Okay, so if I'm going to do -8 times the pivot for row 1, actually I could just do row 1 subtract row 5. Okay, since row 5 divided by 8 is the pivot anyway. So if I just do 8 minus 8, that'll give me 0. 0 minus 0, 0 minus 0, minus 3 minus minus 3 is 0, minus 1 minus minus 1 is 0, 0 minus minus 1, and then 80 minus 80. Okay, so end up with that for my top row. If you didn't follow what I said there, to do it quite quickly, then just crack on with this instruction here. But essentially, PI is row 5 divided by 8, and I'm looking to do 8 times the pivot, which is, rather than dividing it by 8 and then times it by 8 again, I just did row 1 subtract row 5. Row 1 subtract row 5. You can do that. That's also fine. It's the same thing. Okay. All right, row 2. So row 2, we've got the number 2. We're going to plus 7 times the pivot, and the pivot was minus 3/8. So that gives us minus 5/8. We've got 0 plus 7 times negative 1/8, which is minus 7/8. And then we've got 0 plus 7 times 1/8, which is 7/8. 40, previous entry, plus 7 times 10 is 110. Okay. This one here is row 3 subtract 4 times the pivot. So row 3 was negative 1 there. We're going to subtract 4 times the pivot, which is minus 3/8. So that is negative, positive 1/2. 0 subtract 4 times negative 1/8 is again positive 1/2. 0 subtract 4 times 1/8 is negative 1/2. And then we have 80 subtract 4 times 10. And then our final row is row 4 plus 2 times the pivot. So row 4 is the number 1 plus 2 times the pivot, which is minus 3/8. So that gives us a quarter. And we've got 0, previous entry, plus 2 times the pivot, which is negative 1/8. So that's negative a quarter. And then we've got 0 plus 2 times 1/8, which is positive a quarter. And then finally, you've got 20, which is the previous entry, plus 2 times the pivot, which is 10. So that's 40. Okay, so there's my tableau there. And the first objective has now been met, because we can extract that capital A equals 0. Capital A equals 0. Capital P is 110. X is 10. Y is 40, S1 is 40, S2 and S3 are both 0, and most importantly, A is 0. The top row actually reads capital A equals lowercase a, which is what we started with. But that's good, because capital A is now 0. Our first objective is met. We've minimised A, because you can't go negative, because this is simplex. So none of the variables can go negative. So 0 is as small as it gets. And we can see that there's no positive values here in the row, so you can't decrease it any further. Okay, so where are we now? Well, we're at x is 10, y is 40, so we have moved up to this point here. So we're at the point C. Okay, we've moved to here. And at the point C, we can see that the p-value was 110 based on our graphical solution here. Okay, the p is 110. All right, but because we've met our first objective, what we can do now is we can ignore the A column. So don't actually cross it out in the exam, because you shouldn't cross anything out in the exam unless you don't want it marked. And we can cross off the A row. So our first objective is met, so we can get rid of that. And then we can also get rid of this. So that decreases the size of our table to just PXY / surplus and the right hand side. Okay, the A's have been ignored, and that's been ignored. And what you'll find in the exam is the next tableau will be a little bit smaller. Okay, the first objective is met. We now look to solve the second objective. So the second objective is to maximise P. Now to maximise P, we need to choose the most negative value in the objective row. That's the most negative. So we're going to choose to move along S3. Okay. Conduct a ratio test. So 40 divided by a half is 80. 40 divided by negative a quarter is negative 160. And then 10 divided by negative 3/8 is negative 83rds. Either way, those two are negative, so we can ignore those. So this is the only positive number, so therefore this will be our excuse me, our pivot. All right, so let's just finish up this video by finishing off this problem. Row 1, row 2, row 3, row 4, row 5. Row 1 obviously won't carry forward, but this is still being referred to as row 3 from the previous tableau. Okay, so just be aware of that. So I'm going to say that the pivot row is equal to 2 times row 3. Okay, and that's because this is a half and I want to make it the number 1. So I'm going to double everything in that row. So that remains as a 0, 0, 0, 2, 1, 1. Okay, this column's gone, and 80. Okay. The P column is going to remain as 1, 0, 0, 0. We want this to be 0, 1, 0, 0. That's why we've chosen this one as our pivot, which means X and Y are going to remain as 0, 0, 0, 1 and 0, 0, 1, 0. Okay, so it's just these 9 numbers now to fill out, and we're going to do simplex, just as we have done. So let's put the instructions down. So this is going to be row 2 plus 7/8 times the pivot. Okay, get rid of that 7/8. This is going to be row 4 plus a quarter times the pivot. Get rid of that. And this is going to be row 5 plus an 1/8 times the pivot. Okay, so there's my instructions over there. Right. So row 2, so that was a 0, and I'm going to add 7/8 multiplied by the pivot, which is the number 2, so that is 7/4. We've got minus 5/8 plus 7/8 times by the pivot entry, which is the number 1, so that's a quarter. And then this entry here, it was 110, and we're going to add 7/8 multiplied by the pivot entry, which is 80, so it's 180. Okay, this one here, it was a 0, and we're going to add a quarter times the pivot entry, which is number 2, so that's a half. This one was negative a quarter. Oh, sorry, no, it wasn't. It was a positive a quarter. And we're going to plus a quarter times the pivot entry, which is number 1. So that is also a half. And then we've got 40 plus a quarter multiplied by the pivot entry, which was 80. So that is number 60. And then the final row, it was a 0. We're plussing an 1/8 times the pivot row, which was the number 2, so that is a quarter. Then we've got minus 3/8 plus an 1/8 times the pivot row, which is number 1. That's negative a quarter. And then we've got the number 10 plus an 1/8 times the pivot row, which is 80. That's 20. There we go. We are now at the optimal vertex because there's no negatives in our objective row. Okay, they're all positive in there. So we've maximised P. All right, so let's extract the values from this. P is 180. S3, so our surplus, is 80. Y is 60. X is 20. And S1 and S2 are both 0. Okay. Okay, so let's just check that with our graph and see what we've done. We are at the point X is 20, Y is 60, which is here. So we've now made it to our point A, and we've done that by moving in this direction. So just notice what we've actually done is we chose this column, S3, to move in. It's essentially, we are looking to increase the surplus variable. The surplus variable at the previous iteration was 0. That meant that we were on this constraint. And increasing our surplus meant that we are going to move away from that constraint. So we had to move up this line here. And in doing so, we have changed the value of S1 from 40 to 0. Because we were off this constraint, which is what S1 represents, and now we're on that constraint. So S1 and S2 are both 0 at that point, because those are the two slacks for these two constraints. S3, which is the surplus, means that we are off this constraint, which we are, because we've moved away from it, and we can see that X is 20, Y is 60, and at that point P was 180, which was the solution we got graphically. Okay, so that's two-stage simplex in action. I hope doing it in 2D alongside the graph has helped to visualize exactly what is going on. But just to kind of summarize, the first objective is to minimize capital A, which is the sum of the artificial constraints, artificial variables. And that takes us from the origin to the feasible region. In this case, minimizing A took us from O to C. And then the second stage of two-stage simplex moved us within the feasible region to the optimal vertex, and that took us from C to A. Okay. Once you go to the second stage, your table will get smaller because you can ignore all the artificial bits and the artificial objective. All right. Thanks very much for watching. I will be doing another two-stage simplex video. So yeah, I've got a two-dimensional case to come, which will be similar to this one, except there'll be two artificial variables, so you can see what goes on there. And then I'm also going to do a three-dimensional one as well. All right. Brilliant.